Here at Goddard, we're building the 5 X-ray telescopes, or XRTs, and we're also building the XRS, which is one of the instruments that looks at the X-rays coming through these telescopes.
That is, the work is simultaneous, but it's not linked together by schedule. They just all have to be at the spacecraft at the same time.
Most assembly and testing of the XRS instrument is done here in the Cryogenic Integration Facility, or CRIF for short.
At the very heart of the XRS instrument is the microcalorimeter array. This is a very small detector, but it has unique and powerful capabilities. The final steps of its assembly are done in this laboratory right here. So let's go and see what all the fuss is about. This is the XRS microcalorimeter array. Essentially, it's an array of very tiny thermometers designed to measure the temperature increase that occurs when an individual X-ray photon is absorbed.
To detect the minuscule amount of heat given off by a single X-ray, engineers must employ cryogenics, the science of the super cold.
Now, in order to make a good spectrometer, the detector needs to be very cold.
An ordinary object doesn't change much when an X-ray hits it. So making it cold helps in 2 ways. One, it means that the temperature change is a larger fraction of the temperature it's sitting at. And 2, the heat capacity of almost everything goes down very rapidly as you get close to absolute zero. So a little bit of energy causes the temperature to rise a lot. So we have to keep it very, very cold.
We have to operate this detector at 60 millidegrees above absolute zero. So that's what the rest of the XRS instrument does, is it makes this really tiny detector cold.
When you're trying to keep something that cold, you usually have to have a multi-stage system, and we do that as well. There's an outer layer of solid neon. That's 17 Kelvin. That's pretty cold for you and me, but it's still blazingly hot for our detectors. So inside that, there's a layer of liquid helium. And that's helium like in your helium balloons, and that's at about 1.3 Kelvin. And then inside that, there's what we call an adiabatic demagnetization refrigerator, which uses magnetic spins inside actual atoms and aligns them and de-aligns them in such a way to get us down to 60 millikelvin. The XRS detectors are placed inside a dewar. A dewar is like a thermos bottle. If you have a real glass thermos bottle to keep your coffee in, that's a dewar. And it's 2 walls, and in between the walls is vacuum. So the heat can't get through from one side to the other by conduction or convection. It can only get through by radiation, and that's why it's if you look inside your thermos bottle, it's silver, and that reflects the radiation. We have, just a tiny amount of power, and if there's a lot of heat, even if there's just a little bit of heat getting into the system, we won't be able to keep it cold. So you have to be very careful to isolate the inner structures that are very cold from the outer structures, which are not so cold.
Certain portions of the XRS instrument require work in a clean tent.
One of the parts of this experiment is a bunch of filters, very, very thin filters to let the X-rays through but keep out visible light and infrared, that sort of thing. These filters are very, very thin, and even just one tiny particle, too small to see, could penetrate them during launch when it's being shaken around. So we had to keep everything scrupulously clean, which means doing everything that has to do with the inside of the detector assembly in a clean room.
A clean tent works by pulling the air in at the top and passing it through special filters to remove dust particles. This raises the air pressure inside, which keeps outside air from coming in. Keeping the clean tent environment virtually dust-free requires the use of special clothing commonly referred to as bunny suits. It also requires cleaning all items entering the tent and the use of special materials.
This is clean room paper, but when you run it through the printer, you get a lot of toner on it, so you have to wipe it off before you take it to the clean room. Wow. Tedious, but it does come up pretty black, so it's, Yeah, why am I wiping paper off? Well.
Meanwhile, just across the center, another team is building the 5 X-ray telescopes.
X-ray telescope development is a lot like any other instrument developed for spaceflight. We make small components like reflectors and we test them. We make assemblies including many reflectors and we test that assembly. We make the full-up telescope assembly from those and we test it, and we test, and we test. Because you have to know it's going to work on the ground because you can't fix it in space. We're making the 5 telescopes for the XIS instrument and the XRS instrument that'll be on board the Astro-E spacecraft.
The telescope mirror manufacturing process begins with raw materials like the metal foil.
The earliest operation is foil cutting and forming. We have to produce upwards of 10,000 foils for the one mission in order to get the 6,800 foils that we need to fill up 5 telescopes.
The technician puts the foils through a special roller.
This is going to impart the gross curvature that we need and the slight bit of conical shape that we want. And then you'll put that stack inside this little window here. This forming mandrel has a cone shape that is the proper prescription for its place in the mirror. While it's still under vacuum and the atmospheric pressure is pressing them against the mandrel, it takes on the exact shape of that mandrel.
The X-rays that Astro-E2 will observe get absorbed in many materials, including glass and ordinary mirrors. So Astro-E2 and other X-ray telescopes require a unique strategy to focus X-rays onto a detector.
We use an X-ray telescope which depends on a grazing incidence reflection in which the reflectors are nearly edge-on to the X-ray source. The X-ray beam hits the primary reflector, then hits the secondary reflector, and then moves on to the detector about 4.5 meters away. We add a pre-collimator before the primary reflection to block off-axis X-rays. So now they have the proper figure, is what we say. They're curved just right, and they're smooth enough on that surface, but they're still not shiny enough. Then they go down to the replication lab. They've been busy cleaning up the glass mandrels, and then they're put into a gold deposition system, and gold is deposited on that outer surface of that glass tube mandrel. You spray thinned out epoxy on the foil. And once it's in vacuum, that round mandrel is lowered and it just sits on top of the foil.
Maintain my time.
So then we put that mandrel inside an oven and bake it overnight. And it's not a real bake, it's just 40 degrees C. Gold won't stick to glass very well. Through a process that is more magic than anything else, we lift the foil off of the mandrel, and the gold that had been on the mandrel now is stuck to that thin film of epoxy, but the front surface of this foil sandwich with gold on the front has the surface quality of the glass mandrel.